Welcome to Empowered Learning. This is the second video in the video series for integration techniques where we are going over trigonometric integrals. So in this video, we are going to deal with integrals of the type where we have a product of sine and cosine functions, but both the sine function and the cosine function are raised to some power where that power is higher than 3 for each of them. Okay? And so the strategy that we sort of employ for this particular method is going to entail what we did in the part 1 video. And so in the part 1 video, we wanted to break down either the sine function raised to a power or the cosine function raised to the power in such a way to where we could use either U-substitution, or we could use trigonometric identities to substitute. Specifically speaking, whenever we had an odd power for the part 1 video, we wanted to break it out to where we had an extra sine or cosine just kind of hanging out on the outside because we wanted to use that as a means of being able to cover our derivative whenever we do use substitution. Whenever the exponents were even, we wanted to use the reduction formula trig identities to be able to help us out. And so again, we'll be using those same things here. Now, in the case of having a sine function and a cosine function, both powers that are 3 or higher, and they're multiplied times each other, again, we want to look at the cases where if n, in this case, which is our cosine, if it's going to be odd or if it's going to be even, okay? And specifically, what we're going to deal with is cases of, let's say, when this is odd and this is even, and then we're going to switch it and say, all right, well, what happens when this is odd and when this is even? And then we're going to deal with situations where, well, what happens when they're both even? Okay, so those are the 3 different situations that we'll look at closely. So in the case where our cosine is the one that is odd, what we want to do is kind of do the same thing that we did before. Since it's odd, that's the one that we want to break out. Okay, and since we're able to break it out, and we know that we would want to use in this case, u is equal to sine x for the substitution, we don't really worry about this because this is just going to be u raised to some power at the end of the day. So since this is odd, that's the one that we're going to break out. Okay, and then it's going to look very similar to what we saw in the part 1 video. So if we have a situation where the sine one is the one that has the odd power, then of course we just break out sine instead of cosine, okay? And we kind of use a similar strategy there. Now, as an example here, we have sine raised to the 5, cosine raised to the 4, okay? So if I wanted to break this out here, I'll just start right here. Since sine is the one that's odd, I want to break this out as sine raised to the 4 squared times sine. And then just do cosine raised to the 4 like this. And so for here, I want to further, well, actually, let me do it this way. Because sine is the one that's odd here, I know that I can rewrite this, get this going here, as sine squared. Could do that. And we'll keep this as cosine raised to the 4th. Okay. Now, from here we know that sine squared is 1 minus cosine squared. And so now what you see is that we have everything written in terms of cosine except for this sine x here, okay? Now, if you imagine that we were integrating this and we had this dx being multiplied here, then we would have dx here, we would have dx here, and we would have dx here. Okay. So once we have that, then of course we know that we could just use U-substitution here. Okay. So we can say let U equal cosine of x, which means du is going to be minus sine of x times dx. Okay. And once we realize that, then what we can do here is replace our cosine of x here with u, our cosine of x here with u, so we'll have u to the 4 here, and all this will just be 1 minus u squared and squared. So I'll go ahead and just rewrite everything here. And of course, here we have the sine x dx. If we were to rewrite that, that would just be the same as minus du. Okay, so this sine x here, along with that, all together just ends up being a minus du. So all that just gets replaced with 1 minus u squared times u to the 4 times du. And of course, the minus will go on the outside there. And so from here, that's just a polynomial. Of course, we'll have to multiply it out, but that's relatively easy to do, and it's a much easier situation than what we would have had if we would have had to kind of deal with this in another way. Okay, so once you're here, then it's just algebra at that point to get it looking into a form to where you could take the antiderivative of what remains in terms of u, take the antiderivative, and then just back substitute what u was, and you're done. So looking at this the other way, let's say if cosine was the one that was odd, then of course here we'll keep sine raised to the 4 the same, but now we'll break this out as cosine squared of x squared times cosine of x. Okay, and again, this cosine squared is just the cosine raised to the 4 that this would be. So from here, we know that this cosine here cosine squared could be written as 1 minus sine squared of x squared. And so now we see that pretty much everything is written in terms of sine except for that cosine x that's out there. And so now we know, hey, I could use substitution again. So here, imagine again, if we had a dx here, had a dx here, had a dx here, then what this means for us is that we could let u, in this case, be sine of x, which implies that du is going to be cosine of x dx. So what we have here, this sine raised to the 4 of x, all this would just be u raised to the 4. All of this here would just be 1 minus u squared quantity squared. And then, of course, cosine of x dx is just du. So all of this is just going to be du. So therefore, we know that sine raised to the 4 of x times cosine raised to the 5 of x, and I'll go ahead and throw in the dx here, that could just be rewritten as u raised to the 4 times 1 minus u squared quantity squared times du. And again, from here, it's just a matter of multiplying out the 1 minus u squared squared and then multiplying the u to the 4th in. We'll get a bunch of terms that are polynomial looking, and we can just take the antiderivative of those relatively easy. and then back substitute in what u is. All right, so up to this point, we've dealt with situations here, and I'm going to scroll down just a little bit. We've dealt with situations that look like this, where we've had a situation where either m is odd or n is odd, okay? And I'll kind of do it like this. If m is odd, then n is even, or if I was supposed to put, oh yeah, I did have it right. Let me do it like this. This is the way I want to do it. Kind of want to be opposite like this. So if m is even, then that means n is odd. Yeah, that's what I was trying to do. So that's what we've dealt with. So now what we're going to deal with is a situation where both m and n are even. They don't necessarily have to be equal to each other, but they are even. So we'll just say m, n both even. So when we have that situation here, it's actually a much more simple situation to start off, but it gets a little bit more complicated as we move forward. Only because of the fact that we're dealing with the reduction formula, and there's a lot more multiplying that we're going to have to do here. So in essence, what we have to do in this case is basically replace our cosine squareds with 1 plus cosine 2x divided by 2, and our sine squareds with 1 minus cosine of 2x divided by 2. Okay, and again, let's say if we have like sine raised to the 4, then we would rewrite that as sine squared squared, and then take the inner sine squared and rewrite it this way. Okay. Another thing that we will find useful here is if you remember that sine of 2x, that identity is 2 times sine x times cosine x. And if we rewrite that, we see that sine x times cosine x is really just 1/2 of sine of 2x. And I know I've found this to be very convenient when actually working on these kinds of problems, because it really does help to simplify things much faster than just trying to use these two and kind of go brute force at it. Okay. All right, so I do want to show you some simplification examples of that before we get to the examples that we need to do for this type. So if we do this example here, we see we have sine raised to the 4 times cosine squared. And normally we would have this be a power of 3 or higher, but you know, we do see ones like this, so that's why I wanted to go ahead and do it. So here we know that we could rewrite sine to the 4th as sine squared of x squared times cosine squared of x. Okay. And so here, note that we could rewrite sine squared of x, and since both of these are even here, we can rewrite this as 1/2 of 1 minus cosine of 2x, all that squared. And here we could rewrite cosine squared of x here as 1/2 of 1 plus cosine of 2x. Okay. Now, if we rewrite it this way, I can tell you that there's going to be a lot of hard work here. It's not that bad, but the thing is if you can kind of see here, we're going to end up dealing with a cosine cubed of 2x. And again, that's not terribly difficult to deal with, but we want to try to avoid dealing with that if we can. So although this is a way that we can do this, I'm actually going to shy away from that, just because the alternative way that I can do this using this particular identity here will actually turn out to be a little better for us in the long run. So I'm going to stop the video and erase this, and then we're going to break this out as if we want to use this identity, and you're going to see how it actually ends up being much cleaner than trying to deal with this situation here. Okay, so if we're going to use the other identity, the sine of 2x is equal to 2 times sine x times cosine x, and rearrange that for just sine x times cosine x, then what we want to do is break this out this way. So we want to break out sine to the fourth as just sine squared times sine squared. Okay. And then, of course, write the cosine squared there. And here what we could do is we could rewrite the last two factors here to where we write them together like this. Okay, so per our exponential rules, we could rewrite sine squared times cosine squared. It's just sine times cosine quantity squared. Okay. Now, if we do that, then of course, sine x times cosine x, we know that that's the same as sine of 2x divided by 2 quantity squared. And of course, from here, we could deal with this. And we know there's understood 1/2 there, so that 1/2 squared is 1/4. And then, of course, we also have sine squared of 2x. Okay, so at this point, notice that we have a sine squared x and we have a sine squared of 2x. And in order to get this to work for us, we're going to have to decide, do we want everything in terms of just x or 2x? Now, it turns out that if we were to use the reduction formula here for sine squared of 2x, I'm going to make that 2 look a little better here. If we use the reduction formula for sine squared of 2x, what we would end up having is a cosine of 4x in there. Okay, so that would make a bad situation worse. However, if we use sine squared x and we use that reduction formula, we would end up having a cosine of 2x in it. So we want to replace this sine squared of x with the reduction formula equivalent, because it has the 2x on the inside of the cosine function, which will match what we have here. And that'll make the simplification of what we need to do a whole lot easier to deal with. So I'll keep coming here. I'll go ahead and write the 1/4 that's right here out. This sine squared, I'm going to replace this with 1 minus cosine of 2x divided by 2. And I'm going to keep my sine squared of 2x as is. Okay. Now, if I factor out the understood 1/2 in the middle factor, then 1/4 times 1/2 would be 1/8. I would have 1 minus cosine of 2x times sine squared of 2x. Okay. And then at this point, I can multiply my sine squared 2x to both terms. And when I do that, what you're going to see is that I now have what I would be trying to integrate. Of course, if I had the dx here and all that, I would have a situation where I would have two terms, but those two terms would be relatively easy for me to integrate. Okay, and so I'll sort of explain that here. So if I multiply the sine squared 2x times 1, of course I just get itself. And then here I would have cosine of 2x times sine squared of 2x here. And let's try to make that look a little better. All right. So notice here at this point, if we were actually doing a problem here, we would have the dx that's right here. And notice that for this first term, I can now just rewrite sine squared of 2x using the reduction formula. Okay, and this part here will just end up being 1 minus cosine of 4x divided by 2. Okay. For what we see here, we could actually do U-Substitution. Okay. We would let U equal sine of 2x. And then from that, du would just be 2 times cosine of 2x dx. Okay. And notice that we have the cosine of 2x dx right there. Okay. And of course, that dx would of course permeate over to, or distribute over to, both of these terms here. So essentially what I'm saying is that at this point, we have what we need to be able to integrate this if we were asked to do it. Okay. And so what that would actually look like if we actually wrote it all out, it would be 1/8 here times, and we would replace this with 1/2, 1 minus cosine of 4x. And then we'll have minus here, and instead of having cosine of 2x times sine squared of 2x, we're going to write everything in terms of u. And again, I'm going to assume here that I already have the dx in here, so I'm just going to go ahead and write it in. So let's say we have a dx here, and we have a dx here. And I'll go ahead and erase it from here. So if we have that, then we have the situation here where we know that cosine of 2x dx, it's just going to be half of whatever du is. So here we know, switch colors there again. So this is going to be du divided by 2 is equal to cosine of 2x dx. Okay. So we know that we have a 1/2 du here. And since I'm writing in the dx's, I need to go ahead and put dx right here as well. Let's get that looking right. So we got that, and then we have a 1/2 du, and of course, in place of sine of 2x, we're just going to write u. So that's just going to be u squared there. And this is essentially what we would have to integrate. Of course, the first term here would be integrated with respect to x. Second term would be integrated with respect to u. And then once we're done, since we really want everything in terms of x, we would back substitute in that u was equal to sine of 2x, and then we'll essentially be done. Okay. So this shows you examples of how we actually do the simplification for a case where we have an odd and an even power for sine and cosine respectively. Also, what happens when we have even powers, okay, for both of them. All right, so let's wrap up this video by going over a few examples here. So this first example, we want to find the indefinite integral of sine raised to the 6 times cosine raised to the 3. Here we see that, of course, the cosine one is the one that's odd. So this is the one that we want to break out. In other words, we want to break this out as as cosine squared times cosine. Okay. So notice here we go ahead and break that out. And we want to break that out because we know that we could replace cosine squared of x with just 1 minus sine squared of x, which is what you see here. Once we do that, everything is written in terms of sine except for this cosine x dx part. And we know that if we use U-Substitution and let sine equal u, then of course the derivative of sine is going to be cosine, which once we do all the substitution, we know that cosine of x dx would just be the equivalent of du. So all of this is du. We know all of this is just 1 minus u squared, and this is u raised to the 6. So we take that knowledge, replace everything in terms of u, and now you see that we just have a polynomial in terms of u. Very easy to take the antiderivative of. Of course, u to the 6th antiderivative is 1/7 u raised to the 7th. And for u raised to the 8th, it's going to be 1/9 of u raised to the 9th. And then, of course, you see here we're back substituting in that u was sine of x. And you see that this is our answer. Okay. And again, relatively simple to do once you kind of know what it is that you're after. All right, so for the next example, this one is worked out as well, but this one is a definite integral. Notice, again, both of these, in this case, are odd powers here on the sine or cosine. So we could actually choose which one we want to break out. In this case, what we'll do here is we'll break out the sine of x raised to the 5 instead of the cosine raised to the 3. And that's just because we can choose, and I wanted to do something a little different there. Okay, so we want to break this out, so we need to have an extra sine x hanging out. So we need to break this down into sine raised to the 4 times sine, which will end up just being sine squared times sine. Okay, and then of course from here we know that we could rewrite sine squared of x as 1 minus cosine squared of x. And at this point, we're going to let u equal cosine of x. Okay. And of course, from all that, we do the substitution after we take the derivative. So we know the derivative of cosine is minus sine of x. And so when we rearrange everything, we know that minus du is going to be the same thing as a positive sine of x dx. And since we have limits of integration here, we also could rewrite these numbers that are in terms of x to now being in terms of u, just by substituting it into our substitution here for u. So we see we get 0 and negative square root of 2 over 2, or negative 1 over square root of 2, if you want to write it that way, respectively. Okay. So then after that, then it's just a matter of actually going in and replacing everything. So we started off with this integral. This is now everything written in terms of u, where we haven't actually filled in these numbers yet. But in this next step, we actually do that. So you see that we have the negative square root of 2 over 2, 0 here. The minus sign that came from the minus du is now on the outside. And we also notice here that these limits of integration are out of order. Okay, so we have to have the number on top here be the larger number. And since it's negative, then of course it's smaller than 0. So we flip these numbers here. But in doing that, it also makes us multiply by -1, which gives us a positive. And so now we also can go ahead and distribute our u cubed to all three terms here. And you see we just have a polynomial that we have to take the antiderivative of. So we do that and just evaluate it from negative square root of 2 over 2 to 0. And so the rest of this is just me doing all the work to finally get to that final answer. Okay. From that point, it's just a bunch of arithmetic. And we see that we get the answer of -11 over 384. All right, so for the last two examples in this video, I'm actually going to work out some problems from scratch here. So we want to evaluate this indefinite integral, and we see that since sine is the one that has the odd power, that's the one that we want to break out. Okay, so I'm just going to actually do the simplification first and then dump everything in at the end. So we're considering this, and what we want to do is break out that sine of sine cubed as just sine squared times sine. And then of course we'll have cosine squared of x here. And here we want this sine squared from the one that we broke out to be replaced as 1 minus cosine squared x. And we'll say times, and I'm going to move this cosine squared here, and then do the sine x like that. And I'll go ahead and rewrite the dx's in there. Okay? So at this point, we have this set up in the way that we want it. Everything is in terms of cosine except for this sine x dx. So that lets us know that we want to replace u, or do U-Substitution, where we're going to let u be cosine of x. And that implies that du is going to be a minus sine of x dx, which of course implies that minus du is a positive sine of x dx. Okay? So here this means that all of this is just a minus du. This cosine squared is just u squared. And 1 minus cosine squared is just 1 minus u squared. So now that we have all that, we can now say that the integral of sine cubed of x times cosine squared of x dx, yep, sorry about that, pen got kind of out of control there. So here we can just replace this with 1 minus u squared times u squared times du, and we'll put the minus on the outside here. And in doing that, that's going to now make this look like integral of u minus 1 u squared du. And go a little further, this would be u raised to the 4 minus u squared du. And so now at this point, it's relatively easy to integrate this. We take the antiderivative of both terms. The antiderivative of the first term is u to the 5 divided by 5. Antiderivative of second term is u cubed divided by 3. And then, of course, we add the integration constant at the end. And then finally, what we do is substitute back in what u was. And, of course, u was cosine of x here. Okay? So this would be 1/5 cosine of x raised to the 5 minus 1/3 cosine cubed of x plus c. And that would be our final answer for this example. All right, so for our final example, it turns out that we've kind of already done the heavy lifting for this particular problem already. If you remember earlier in this video, we actually worked on simplifying the integrand part, the sine raised to the 4 times cosine squared. And so now that we've actually done that, we're just going to go see where we left off and pick that up and go ahead and finish this problem, since we've kind of already done the heavy lifting there. So let's go back and see what we had. All right, so this is where we were when we were working on this expression here. And notice that we said that since both the sine and the cosine both had even powers, that we wanted to kind of take a different approach and use other trig identities other than just the ones that come from a fundamental identity. And so here we decided that instead of using the reduction formulas for both sine squared and cosine squared, we would use the variation of a theme on this sine of 2x is equal to 2 sine x cosine x. Okay, so we decided to use that and rewrite it as sine of 2x divided by 2. So in doing that, of course, we did all the heavy lifting, and we saw that what we ended up with is right here. So what we're going to do is make note that our u here is sine of 2x, and we're going to write this down where we are in the actual problem that we need to solve, and we're going to go ahead and finish this up now. All right, so I've taken the time to go ahead and write down what we had, and I'm also going to write here that u was equal to sine of 2x. So we're going to keep that in mind because we'll need to substitute that back at the end. So now that we have all that, I'm going to write this as two separate integrals here. So what we'll have is this 1/8 times 1/2, which will be 1/16 integral of 1 minus cosine of 4x dx. Then we'll have the same 1/8 times the negative 1/2, which will be a negative 1/16. And then we'll do the integral of u squared du. So from there, we know that the antiderivative of 1 with respect to x is just x. The antiderivative of cosine of 4x with respect to x is just sine of 4x divided by 4. And 1/16 here. And of course the antiderivative of u squared is u cubed divided by 3. And since this is an indefinite integral, we will do the plus c at the end. And then all we need to do, of course, is back substitute what our u was, which was sine of 2x, and then just multiply these constants on through. So I'm going to go ahead and do this part now. And we'll have that over 48, and this will be sine cubed of 2x here plus c. And so this should be our final answer for this particular question. And just to make sure that is a minus sign, not an equal sign. All right, so this concludes the part 2 video on doing trigonometric integrals. So in the part 3 video, we're going to study combinations of tangent and secant to where their powers are both either 3 or higher.